Good afternoon, everyone. Hi, I am Varun Kumar Paliwal. I am from Mindteck, and today we are here to uh, uh, present the PPT. So before going there, I am introducing myself and my co-host Ankit. I am working in Mindtech as a technical lead, and from past 8 years, I am working in a storage domain and embedded domains. My co-host is also working in Mindtech as a senior software engineer, and he is working from last 6 years in framework development and storage development. He is an expertise in Python. Now we will go and talk about our today's sessions, which is uh, on SSD. So today's topic we took is SSD read latency optimization. As we know from last few decades, SSD is more come into the picture as compared to HDD, and SSD is more SSD is more providing the optimization and storages. When we talk about SSD, it is fast compared to the SDD, but it's all are the benefit of the SSD. When we talk about what are the disadvantages of SSD, which we see that there are read latencies, which we see when we SSD get older. So how we make those read latency optimized, we are uh, we are going through that today in this slide. So me and Ankit will take you there and we'll discuss more how we optimize the SSD read latency. So in today's agenda, first we discuss how SSD is organized. Then we go through and see that how read operation is happening in NAND. As we know that in SSD consists of NAND, and through which we are able to do the read and write operation. So we will more focus on the read operation in the NANDs. Then we will see that if read failure happen, that then how read retry operation will happen, and what are the performance overhead will come as part of these read retry. By seeing the performance overhead, we will discuss how we will get resolve these overhead as part of this topic. To resolving this issue, we have selected two features. One is cache read feature, another is ECC capability margin. On these features, we have developed two new mechanism. One mechanism is pipeline read retry, which is dependent on the cache read feature. Another mechanism is adaptive read retry, which is dependent on ECC capability margin. And this whole topic is more driven by one of the research paper that is published by the June. So now I will call my co-host Ankit and take you through how SSD is organized and how read operation is happening in NAND.
Yeah, thanks, Varun. So, hi, let's move on to how SSD organized or how SSD internal architecture is look like. So, if you zoom into the nanoscopic view of uh, an SSD, this structure is look like, which is called VNAND, and that holds all the data in SSD. So, every data is stored in the quantity of electron inside the memory cell called charge flash trap. So this is the structure of charge flash trap. And in each cell, we can store the information by placing different level of electron in charge trap, which is the key component inside the memory cell. So this is the charge trap, and where we can store by trapping this charge inside this memory cell. So in each cell, we can store the information by placing the different level of electrons charge there, which is the key component of the memory cell. So older technology could only hold out to 2 bit of information, either 0 bit or 1 bit. With the evolution of technology, one memory can store up to 8 bit of electron, and with the help of cutting edge technology, it has capable to store up to 16 level of electron. So now storing the only single bit information, it can store 3 bit information or more. So for this exam in here picture, we can see the single cell are storing 8 layer of data, like from 000 to 111. And this is the key to this charge trap is that it is specially designed so that after it gets charged with electron, it can hold electron for decades, and which is how the information is stored or written or to SSD. To read the information, the electron charged is measured and amount on the charge trap, and which is unchanged over the time. And through this bit line, it can uh, read the value whatever the charge status. So, and to erase the content in the memory cell, all the electrons are removed from the charge trap forcefully and retaining it to the lowest level, which is 111. So, as these memory cell are stacked vertically in the form of V NAND. So each cell can be stacked in the form of V NAND, and one vertically stacked cell is technically called a string. So when the information is written to or read from a string, only one cell can be activated at a given time, and the information can be transferred from a memory cell uh, using this bit line. And this memory cell are controlled by control gates. So when a string is stacked horizontally in the form of uh, it forms a page, and the whole structure is called row. So where each string has its own bit line to transfer the data, and every cell in the single page share the same control gate, so that all the cell can be accessed in same time. When when rows are stacked together, it form a block, and column are connected with the same. Each column is connected with the same shared bit line, and bit line works as a highway where it transfer data from memory cell or read the data from to memory cell. So another control gate is attached to this bit line to manage the row, and which is called bit line selector, as we can see here. So there are basically two selectors. One is bit line selector and one is control gate. Using this at a particular time, a single phase can be activated, and with the combination of bit line selector and control gate, this combination is known as row decoder. So a common SSD chip contains around 96 to 136 layers, and also 30,000 to 60,000 bit lines. And it also contains like around 4,000 to 6,000 blocks alongside with the its bitline selector and control gates. So at the single time, all the 30,000 cell on a page can be activated, and data can be written or read through using the page buffer, and all the data can be transferred using this bitline. Now this is the how memory VNAND memory cell look like. So this is VNAND memory cell, and we have the row decoder, which is managed to activate one page at a time, and the page buffer and some peripheral circuit, which is used to manage how the data will be written and organized. Now let's move on to the how NAND flash basically read operation does. So NAND flash memory store data by adjusting cell threshold voltage. So this figure show a part of threshold voltage distribution of a page where each threshold voltage stage can distinguish by using the corresponding read reference value. So we can see here there are different read reference value, and these are the threshold value where each track is here. So if we apply a certain read reference value to a target cell to read some data, it would operate as a resistance for lower than the voltage, and it will act as a open gate when the voltage is more than that. We can specify any threshold voltage cell if we read uh, the cell twice with using two read reference positive values. So for example, the cell PX would operate as an open switch if we sense the page using the left read, but cell operate as a open when we read from the reference voltage. So in contrast operation, all the other cell would not change the consistency, operate as either resistance or the open switch. So in NAND flash memory, a variety of source including program interference, read disturbance, and data retention loss introduce a bit error in the stored data. So a figure show that the threshold voltage distribution of a flash cell in a single VNAND, uh, and how it is affected by various uh, error sources. So reading or writing a program, a flash cell slightly increase the threshold level to the other cell in the same block, as we can see here, and that is called read distribution retention age. And also program the cell loses its voltage over the period, and which is causing the retention loss or interference distribution. So if cell threshold voltage level moves beyond the reference voltage value, bit error occurs and a cell data is sensed to be different from the originally programmed into it. So prior work shows that the retention loss is the dominant source of error in 3D NAND memory, and memory experience 40% less programming interference and 96.7 weaker read disturbance, while it suffer from large number of retention error that occur faster. So a flash cell become more susceptible to error as it experience more program and erase cycle. Uh, so program and erase cycle to write or read the data to a cell. So the high voltage applied to the word line and subtract the during the program, and erase operation damage the flash cell tunnel oxide, which is also cause charge trap to leak more easily electrons. So after a certain number of P cycle, flash cell is worn out and it cannot be used longer. So it can so it loses the electron, it cannot retain the stored data for the required age, and the multi cell level technology aggravate this reliability problem in NAND. So in the second figure we can see that this margin is like very less, and it is more prone to the errors when a cell loses its electron. So to correct this problem, we have two major functionality which is applied to the SSD. One is called error correcting code, which is short form as ECC. So to guarantee the reliability of the stored data, it is common practice in modern SSD to like implement ECC, and ECC can detect the correct bit error within unit of data, called code word, by storing the redundant bit, that is called ECC parity, along with the original data in order to use the redundant data of error correction. So typically an ECC engine exists in the flash controller, and when SSD controller issues a read request, uh, the request handler send a NAND command to the NAND flash chip, and this reads a page and which is the transfer the data to the ECC engine. And after the ECC, finally ECC engine decodes the transfer data and trying to correct all the errors in the page. However, if the number of raw bit error is higher than the ECC correction capability, it leads to that uncorrectable error in stored data. So this is the reliability problem in the flash. To address this in modern SSD, commonly adapt a mechanism called read-retry, where it reads the page and adjusts the read reference value to the optimal value. And using particularly adjust read reference values significantly decrease the number of raw bit errors reading in the page. But unfortunately, this read retry also increases the read latency. To mitigate this problem overhead, read retry prior work has been proposed in various technology that is basically aimed to reduce the number of retry steps accurately, predicting the voltage near to the optimal value. So the basic retry mechanism gradually adjusts the read reference voltage until it find one is uh, close to this optimal, and which is also allowed to skip the unnecessary retry step. But however, the threshold voltage quickly and significantly changed over the modern NAND memory, and so the read retry is like fundamental problem in SSD, and which is hard to eliminate. So this is how read retry performance overhead comes. So to reading a page which contains three steps. One is like page sensing, which we represent as TR for this case, and the data transfer time, which we represent TDM, and the error correction decoding time, which we are representing here with the TECC. So if the error bit in the page is less than the error ECC capability, like in this case it is 72, so directly the page is read and it will transfer to the SSD. But if this ECC value, if the error value is more than the ECC capability, like in the second case it's 232, it is keep on retrying to correct the bit, and with the over the time it reduces the error in the page. And once the error is less than the ECC capability, it will uh, send the page data back. So this was the original time which is you required to read a single page if there is no error in or no error, or it is the error is less than ECC capability. But as we are keep on retrying, so it is linear multiplication of all the three TR, TDM, and TECC, which is required for T latency. So to overcome this problem, I am over to Varun to present the solution to reduce this read latency.
So as we know that in SSD, when it get older, the read retry problem will get increased and it will become a more overhead as explained by Ankit. So to overcome this, we will go through to understand two basic feature first. One is cache read feature, another is ECC capability margin. So first we will look how cache read feature works. So as we see in the diagram, so in A diagram, we are trying to read two pages. Okay, so in page A, when we are completing the transfer of data of the page A, at that point of time, we start reading the page B. So this way, we are saving some cycles in the page read option, and this scenario will be called as a page reads. Okay, now when we have to implement cache reads, so we have to start the page B read as is shown in figure B when the data transfer of the page A started. So in this way, we are saving more cycles in the cache read because we are starting a little bit more earlier page week compared to a figure A. So in this way, we can reduce the latency of a page read by using a cache read command as explained here and as shown in the figure. Now we will see the other feature which is ECC capability margin and which we taken into the consideration after studying the SSD behavior. So as we know that ECC capability margin will occur when a read retry appears. And whenever read retry appears, this ECC capability margin will be a very large value. Now, this will be sound a contradictory. If it's a large value, then how read retry is occurring? The thing is here, the page RBI, which is we call as a row bit error rate, that will get exceeded with the ECC capability margin. That means there is a no ECC capability margin left. That's why read retry occurs happening. So when a read retry operation succeeded, we eventually say that the page was read successfully without any uncorrectable errors, which means that there is a positive ECC capability margin exists in the final retry steps. Okay, so now by understanding these two concepts, we concluded two things, and on that basis, we can conclude that ECC capability margin is very large. First thing is, in modern SSD, we will use a strong ECC that can store several tens of row bit error in a code block. So this way we know that the ECC capability margin is large because with the row bit error rate in a code board is directly dependent on the ECC capability margin as explained in the second point. Okay, the second step, which is that page can be read by using near optimal V reference value that drastically decreases the page raw bit error. So by using these 2 points, we easily concluded that ECC capability margin is very large. Now, by both features understanding, cache read feature and the ECC capability margin, we will understand what changes we introduce and how read retry latency is decreased. First, we will go through pipeline read retry, which is more based on the cache read feature. And as we can see in normal scenario in figure A, that in normal scenario, when a read A is getting failed, we try the read retry steps. And this will happen till ECC success will not happen. So in this figure, as you can see, till the retry step will not complete it. Like retrieval is not getting completed till we are not starting the retry 2. So this way we are taking a lots of latency. Okay, now how we can reduce it? As we can see in the cache read figure method, that we start this retry mechanism once the retry mechanism previous one transfer of that mechanism get started. So basically, when you are retrying the page and transferring of that one started, that point of time we will start the next retry cycle already. That was explained in the second figure. And as you can see here, when a ECC fill happen on the normal read page, we are trying to do the normal page read in the first retry step. But from the secondary retry step, we are applying a cache read. And when we are applying a cache read here, we can see that we are saving this much cycle. So in the end, we are whenever we got the ECC success, we are saving this much cycle. Now here is the catch that once we got the ECC success, till that point of time, we already started a one more retry step, which is not required now. So how we can stop that? For that, we have to implement a new feature that is called a reset. So as it is, you get the ECC success, we will click on the reset and now the NAND will know via SSD controller that we click on the reset, so we don't have to read this retry step. This is unnecessary. So this way we are saving this much cycle compared to the existing redrive mechanism. And that same thing we are trying to explain here via formula. So previously we know that number of read retry step is multiplying with this whole T read, which is TR plus TDMA plus TECC. Okay, but now in the cache read, we are multiplying this and read retry with only page sensing, not with the DMA, which is data transfer, and not with error correction code. So in this way, we are actually saving and read retry -1 into TDMA plus TECC. So this much cycle we are saving by using this mechanism. So now the question comes, we are seeing the positive side and we are saying that this much latency we saved it. But what are the overhead of using this mechanism? The overhead of this mechanism will not be there on the NAND flash chip. And this mechanism is far better than the existing read-retry mechanism. But to implement this mechanism, we require a slight modification in SSD controller. As we are as we are talking two new feature. One is cache read, another is the reset. So to implement these two commands in the SSD controller or firmware, we have to require a slight modification. Either we can do in SSD controller or we can do in the firmware. So these are the overhead are coming to implementing this pipeline read-retry mechanism. Now we will go ahead and we see that by understanding of the cache read and ECC capability margin, by both concept, how we can make this concept more better, and that we will know in this mechanism, which is adaptive read-retry. So in adaptive read-retry, we require some prerequisite data, and that prerequisite data will be provided by the SSD manufacturer, and that data we will call as the read timing parameter table, which we call also as a RPT table. So what exactly RPT table consists? So RPT table consists PEC. PEC here is program erase cycle. How many program erase cycle happens in SSD? And what is the retention days for the SSD? That means we can understand that how much older are we having a SSD. On these two terms, we are calculating one timing that is called the T pre-charge. Now, T pre-charge is required to read the data properly without any error. That T pre-charge we required it. So this table provide this T pre-charge on basis of PEC and T retention data. Now we will see how adaptive read-retry use this table and go ahead. So first we opt the T pre-charge by the RPT table, which will be required more to read the data properly. Okay, now read failure happen. We get here once the read failure happen of the page, we opt the recharge of value. Now after opting this value, what we will do is whatever existing recharge value is there, that we will store locally, and we will replace that SSD recharge value with this value. Okay, so by using set feature command, we will do this thing. So that will happen here. So first and second step will be implemented here whenever any page failure occurs. Now retry will start. So once retry will start, we will again follow the cascade mechanism. So retry one happen, ECC failure happen here, and we know that whenever cache read implemented at that point of time, whenever read retry first started, transferring of that read retry, we start the next read retry. So we are doing this only in the third step, and this way we will be doing the read retry till we did not get the ECC success. So again, same thing. Once we got the ECC success, we will do the reset again. Once reset happen, we will implement one more feature again, that is set feature. Why this required here? Because in the second step, we change the original value with the RPT value. So now we have to replace the original value here with the we have to remove the RPT value and put it the original value, so that after this read retry successful happening, we can do other scenarios, read or retry, whatever required, that can go in a smooth way as it is required. That's why we are setting feature here and we are just going with the old value here. Here we are just seeing that different mechanism as we explained here, where optimal TR will be used. So here deep recharge will be used, okay, for that one. So that was replaced here everywhere. Okay, now by the formula we see that how the changes happen. So as we can see, if we just talk from here to here, this is the pipeline read retry. Okay, now pipeline read retry, when we talk about, that was multiplied with the rational ratio which will be required to replace this value. Okay, and t set, which is required to set this feature. Okay, what all time is happening to setting the values, that timing we are adding here, which is very much minimal compared to this value. So this way we are saving many much again here, and raised to power and read retry minus 1 into TDMA plus TEC. This much cycles we are again saving it here. So this mechanism is also far better compared to the existing read retry. Now what are the overhead of this mechanism? So we have to require a small change in the SSD controller to adjust the key PRE based on RPT. And we have to store this RPT in a specific page of the NAND flash chip, so that at the boot up time from the NAND flash chip, we can copy this data into internal SRAM and DRAM, and then SSD controller can quickly access this RPT table once a read retry. So this much overhead we are seeing using this technology. Now we see that how these concepts giving the results. So as you can see here, we are talking about program erase cycle here. Here 0K, 1K, 2K. These are the retention one. How old are the your SSD controller? That is 3 months, 6 months we are talking. These are the stages on different temperatures of the SSD we are taking this data. And what are the response time when read retry appear. So we are compared this separately, pipeline read retry, separate adaptive read retry, combination of pipeline and adaptive read retry, and no read retry. So as you can see in all the graphs, no read retry is always a best. But what happens if read retry is happening? So whenever read retry is happening, the combination of pipeline and adaptive read retry is giving the best data if we individually put that one compared to that. That's why using these two technology, putting together, give the best data, as we can see from these response time. And this response time was taken by the, or I can say this full research was influenced by this research paper, reducing SSD read latency by optimizing read retry. And we also gone through these some of the reference to understand that how read retry is existing read retry is giving first scenario and how we can make it better. So this mechanism is the far better solution right now present in the market. So that's why we can say that whatever technologies we talked about, these are the best right now. Now, as part of the Mindteck, we work on SSD and storage domains. Mindteck is providing services from last 30 years to their clients, and from last 16 years, Mindteck is working in the storage domains. We have a virtual both install You can go there and see our uh, see more information about Mindteck. If still you have more queries, you can mail us and ask your queries. So thank you to given this opportunity to share our thoughts on these topics. And if you have any queries, please let us know. We would love to help you guys and guide you how we can make it better, our solution, or how we can implement it. Thank you from our side.